All right, so I guess it's time to start, or something. What are you all doing here? So how's everyone doing today? Yeah? Brain full of all kinds of good stuff? Okay, well everyone roll for initiative, because we're going to talk about Dungeons, Dragons, and graph databases. But before we're going to talk about that, I'm going to talk about myself. So my name is Royse. I'm a developer advocate at Redis. There are three things on this slide that matter. One of them matters to you all in the audience. One of them matters to me, and one of them matters to my boss. Any guess which thing matters to my boss? There we go. He wants you to know, and honestly, I want you to know as well. Redis, how many here have used Redis before? Practically everyone. How many have used it for something other than a cache? Like 6. Well, Redis is more than a cache. We want you to know that. One of the things I'm going to show you today is graph databases. There is a graph database feature available in Redis Stack. I'm going to show you that, but it's mostly just going to be about graph databases and Cypher queries. But my boss wants you to know, and I want you to know that Redis is more than a cache. The thing on the slide that matters to me is the Twitter ID. So I measure my value as a human being based on the number of people who follow me on Twitter. You can help me monetize my narcissism. So thank you for your support. And the thing that matters to you is that GitHub URL right there. So I've got sample code that you can play with. If you go to github.com/GuyRoyce, you can go play with that sample code. And don't worry, that URL will be at the end of this talk too. And so I'm a developer advocate. This is what I do. But I'm also a big fan of Dungeons and Dragons. So I thought I'd share my character sheet. You can see that I have an intelligence of 8 and a wisdom of 8, which is not very good, and a charisma of 16, which means this talk is going to be all sizzle and no steak. And as a player of Dungeons and Dragons, I've got a particular problem. And that problem is that I need to level up my character as fast as possible. And in order to do that, I have to go to the dungeon. And in the dungeon, there are various rooms and chambers and places to explore. And in there are monsters which I can kill and steal their life essence, known as experience points. And there is treasure to be taken. So the experience points helps my character become more powerful. The treasure lets me level up my gear, and then I can play the game to its max. But the problem is that the dungeon isn't set up for my convenience, right? The monsters in the rooms and the treasures are all laid out in a confusing way. And I need a way to find a good path through there and find the best rooms that I need to go to first. And so I thought, well, I play D&D, but I'm also a developer. I should build a database that has all of the information about my dungeon in it, and then I can do queries against that database and find the best rooms to go to, the ones with the best monsters and the ones with the best treasure. And my first instinct was probably like everyone's first instinct. I could use a relational database with the tables and the rows and the columns and the ones and manys and all of that. But then I thought I could use a graph database with its nodes and its edges and its properties. And that's really what this talk's going to be. I'm going to show how to model this dungeon, how to query it using SQL. Quick show of hands, is it SQL or SQL? I say both, so I'm always wrong. But we're going to show how to do this with a relational database, how to query it and how to model it. And I'm going to show how to do it in a graph database, and we're going to compare and contrast. And so you can, if you know your way around SQL, which I imagine is probably everyone, or nearly everyone, right? SQL is the only language that I learned in college back in 1992 that I still use. So, and we're going to compare and contrast. So if you're familiar with SQL, you can learn about the graph parts. So we're going to start out with a little bit of what the heck's a graph database. This is the part where when someone says, database, I thought this was a GraphQL talk. If you have that thought, don't worry. You're in the wrong place, but you're in a great place. Because GraphQL is a query language that queries object graphs, and a graph database is also an object graph of sorts. And so GraphQL is actually a good abstraction layer for querying a graph database. So it's not about GraphQL. That's an API interface querying language. This is just a database. but it's still really cool. But what's a graph database? But to talk about what's a graph database, I need to say, what's a graph? Now, some of you may have very mathematical backgrounds and have taken graph theory at university. I have not. I am a little bit of a noob. Many of you may not have this background. So we'll go sort of a little bit of a layman's introduction, an introduction to graph theory for the laity, right? If you're not particularly mathy, then this is for you. If you are very mathy, then you're going to find out everything I'm about to say that's wrong. But it's true enough. So a graph is a mathematical structure made up of nodes or vertices and the relationships that connect them, or the edges. They can be used to model things like social networks, like maybe like following each other on Twitter. They can be used to model transportation networks. You can model all sorts of things with them. And you can even model like geometric shapes. This 20-sided die, which has conveniently rolled a 2, but it's showing the 20, has a vertex or a node. That is the point of that shape. And you probably remember this from geometry class. And it has an edge, which is, well, the edge, or the connection. And so you can use graphs to model all sorts of things. The simplest graph is a null graph. Very exciting. Moving on. Let there be light. So let's add some nodes to our graph. This is still not really what you would think of as a graph, like there's no relationships, but this is still a perfectly valid graph. An empty graph is a valid graph. A graph with just nodes is a valid graph. They don't have to have relationships. So here we have a set of nodes. We know they exist. We don't know much about them, but there are nodes. Still not a very interesting graph. You could use it, but there's not any relationships. So we'll add some relationships to our graph, and we'll see that this graph is starting to turn into something a little more, well, graphy. Now, like nodes A, B, and F have a relationship. They're connected to each other. So those two vertices have an edge connecting them. I guess this is coincidental, but I guess they're best friends. You can all say boo now. Yeah. It was a terrible, terrible dad joke. But by the way, how do you know when a joke is a dad joke? Because it's terrible. Yeah, good answer. It's a better answer. I was going to say, because it's apparent. I was like, I'm out of here. Yeah. So, but anyhow, so we've got some relationships here. You know, these D, A, C, and G are all connected together. B and F are connected together. E's out there by its lonesome. But we're seeing some relationships here. Portions of this graph are what we would call isolated. So node E is isolated. It's not connected to anything else. It's not connected to the larger graph. And actually, the subgraph B and F here, they're isolated as well because it's not connected to the rest of the graph. And I suppose even the main part of the graph would be considered isolated. Isolated just means it's a subgraph that's not part of the larger graph. And so if your graph is not connected, by definition, all of the parts are isolated because they can't reach each other. There's no paths connecting them. There's no edges connecting them. If we add some more connections here, we now have a graph that is connected. This means that every node has a path to another node, directly or indirectly. So I can get from node D to node F by way of A and B, or by way of A, C, and B. I've got a couple paths that I can take. And when a graph is in this state, it's called a connected graph. You can also have a fully connected graph. I'm going to show a subgraph here. A fully connected graph is when a node in the graph connects to every other node in the graph. So if you have 3 nodes, then you're drawing a triangle, right? If you've ever seen those network star diagrams where you have like all the nodes in the network are in a circle, and then there's a bunch of chords going across it, connecting every node to every node. Like if you imagine a pentagon with a 5-pointed star in the middle of it, that's a fully connected graph. This graph is also undirected. The relationships have no, well, directionality. What do I mean when I say directionality? So an undirected graph is like Facebook. If I'm friends with you on Facebook, then you're friends with me on Facebook. It's a mutual thing. There's no directionality. We're just friends, right? I'm picking on you. Thank you. A directed graph has a natural direction. I can't think of any other word other than direction to describe directionality, but it has a direction to it. And so it's more like Twitter. So I might follow you on Twitter, unlikely, but hopefully you're following me on Twitter. And so that following, I follow the audience member is a directed relationship. Another example of a directed relationship would be like with genealogy. My mother bore me. She gave birth to me. And so that relationship has a natural direction to it. If you flip that arrow around, it doesn't make any sense. So some relationships are directional. When we're talking about graphs and the nodes within them, these nodes can have degrees. The degree of a node is just how many connections it has, how many relationships, how many edges it has. So node A here is got 3 relationships. If you have a directed graph, you can also refer to an out degree, which is outbound relationships, and an in degree for inbound relationships. And there really aren't any rules with what can connect to what in a graph. You can pretty much connect anything to anything. And so nodes can connect to themselves. They can connect to each other multiple times. You can just do what you want. It doesn't have to be, oh, I dropped my pointer. There we go. That was the most exercise I've gotten all week. Oh, my back. Yeah. They can connect anyway. This particular graph here is nice and neat and fits on a flat screen because I wanted it to be nice and neat and fit on a flat screen. But there's no reason why node B couldn't connect to node D, or the lines can cross. It's not like Ghostbusters. You can cross the streams. It's okay. So anything can connect to anything. A graph database, then, is when we take this graph structure and we lay data over top of it. So the nodes become nouns in our system. They become things we care about. So they become rooms in the dungeon and monsters in the dungeon and treasure in the dungeon. And we hang data on those nodes. So they'll have a type or a label, more than one label, actually, potentially. Like we have a monster here and a room and a treasure. And you can have properties on those types, or properties on those nodes. So the monster here is named Alice the Elf, has a challenge rating of 7, and is worth 350 XP. Down below, we have Bob the Ogre. He has an ID of 5, challenge rating 5, XP of 250. So we're hanging data on these things. Fun fact, well, at least for me, is that Alice and Bob, aside from being sort of like the default names we always pick, happen to be my grandparents' names. Which is kind of, it's always sweet when I give this talk because I think of my grandparents and how much of an elf my grandmother was and how much of an ogre my grandfather was. No. Actually, he wasn't an ogre. He was a very, very nice old man. And I miss him very much. But this is a graph database. You're relaying this data on top of the nodes. And then the edges can also have a type saying this is the nature of this relationship. And you can hang data on those as well. And when you're all said and done, you've got this graph that kind of looks like what it is. Like it's matching my problem domain very intuitively. I've got nodes, which are rooms. I've got all these nouns that are nodes, and I've got all these verbs that connect the nodes together. And we end up with a beautiful database worthy of Mordor. A couple of notes on this, and sort of a summary. Nodes represent items, and I generally find that they tend to represent nouns. They can have one or more labels or no labels, like monster or room or treasure. And they can have 0 or more attributes, just key value pairs that you tack onto them. And a node can stand alone. It can be out there hanging out in space without any relationships at all. No man is an island, but a node in a graph can certainly be an island. The relationships connecting the nodes represent those connections between those nodes. They connect 2 nodes and only 2 nodes. They have a type, and they have a direction. And they can have attributes as well. But most importantly, they cannot exist without nodes to connect. By definition, an edge is the connection of 2 nodes. And so if you delete a node from a graph database, all of its edges go with it, because there's nothing for it to connect to. So if you put a lot of data in a relationship and then the thing it relates to goes away, then that data goes away too. And I think they tend to read best like sentences, where you've got a subject, a transitive verb in the middle, and a direct object. So the room contains a monster, and so room contains monster. Generally, I find my relationships are verbs, and my nodes are nouns. Not always true, but usually true. It makes good semantic sense. So, now that we all know what a graph database is, enough theory. How do we actually do this? Right, we're developers. We want to get down to where the rubber. I was going to say where the metal meets the road, but that's mixing my metaphors. It's where the rubber meets the road. Because we've still got a problem. Well, I've still got a problem. I still need to find the rooms with the best monsters and the best treasure. And I haven't really decided if I'm going to use a relational database or a graph database. Spoiler alert, I've actually decided. So, how do we talk to a relational database? SQL. Like I said, first language, the only language that I learned in college that I still use on a semi-regular basis today. We use SQL to query relational databases, select star from users where clue greater than 0. Right, that sort of query. A comparable language for querying graph databases is Cypher. This was created by the fine folks at Neo4j, and Redis Graph has gladly used it to build our own graph database in Redis. And Cypher looks like a cross between a query language and ANSI art, or ASCII art. Because at its heart, it's got these pattern matchers. And so in our little Cypher query here, we say match, and then we got this little query thing that has got like parentheses and square brackets and little arrows and stuff on them. And then we return the elements that we've matched. And this matching pattern is really, I think, the heart of the Cypher query language. So this is a pattern that matches rooms that contain monsters. This little bit here matches anything, any node in the graph, any node in the graph with a label of room. And it assigns it to that variable r so that we can refer to it later in the query. And you'll notice that it's in parentheses because it's round, like when we draw a circle on a whiteboard for our node. Over here, we're matching a node with a label of monster, and we assign it to the variable m. And here, we're matching a relationship with a type of contains and assigning it to a variable c. And here we've got square brackets, just to distinguish it from the parentheses. But you've got dash and then dash greater than. It's literally drawing an arrow saying, this is the direction of the relationship. So we got round node, arrow, and then it's probably backwards from what's on the screen, isn't it? But we have an arrow pointing in the direction of the relationship. And so we can match on that pattern. And so we can use these patterns to create nodes and relationships and to query them. So let's go through all the classic CRUD operations. Create, read, update, and delete. And we'll look at how we can do that with SQL, and we'll look at what that looks like with graph. So if we've got a rooms table in our relational database, if we want to insert something to it, we use an insert statement. You've probably seen this before. Insert into rooms your field names, and then provide the values. And it's worth noting that one of the assumptions here of this insert statement is that I have a rooms table created, and that it has a schema. So we have a table in place already. I'm not talking about creating the table. I'm assuming the table's been created already. If we want to create a room in our graph database using Cypher, we use the create statement, and we provided a pattern for the thing we want to create. So we want to create a node with a label of room and assign it to the variable r. And this does not have a schema. It's going to have whatever properties we feel like giving it. And so when we see after the create, we say set, and then we use that variable r, and we'll set the ID to whatever we want the ID to be, and the name to whatever we want the name to be. So here we've created the statue room with an ID of 1. And so we create that room, and then set the properties on it. This is one of those things where some people are like, but can I define a schema in my graph database? No. You define the schema in your code, because your code enforces that. Whereas in a relational database, your schema is part of that. Some people like that, some people hate that. It's kind of like how some people like strongly typed languages and weakly typed languages, they have their pros and cons. This is one of those trade-offs. I like schemaless stuff. I also like JavaScript. Don't judge. I go home and cry at night. But so this is how you do a basic create. If we want to read what we have just created, the first thing you learn in SQL class, select star from rooms, select keys from room where, or select fields from room where key equals whatever. To query our graph database, we're going to use the match command. So what match does is it says match this pattern in the graph. And we're saying match anything with a label of room that's a node. So any node that has a label of room. And then we'll assign all those nodes the variable r. This will just return all the nodes with a label room. And then we can put a where clause on that to filter it down, and we can return it. So match room where ID return. So this match where syntax. Now, I kind of stress the match where syntax because it's going to repeat. This is one of the things I kind of like, is that it's more, like one of the things about SQL is it's always been kind of arbitrary in the different syntaxes you use, depending on whether you're inserting, updating, deleting, or querying. And the graph, the Cypher here feels a little more consistent. So we're matching the room where the ID, returning it. When it comes time to update a room, we do an update statement. The statue room is becoming a statue hall. It's getting an upgrade, it's getting more statues. To do this in Cypher, we match where again. So we match room, assign it to r, where r.id equals 1. And instead of returning it this time, we're going to set the property that we want to change on it. So now we're going to change the name. It's worth noting here, because there's not a schema, I could add new properties here. So if I decide I want to have rooms that are trapped, I could say like set r.trapped equals true. That room would now have a property of trapped. Other rooms that existed already would not gain that. There's no schema. They just wouldn't have a property at all. And so, but that's workable. You know, it's like trapped true or trapped false or trapped, well, I guess undefined since I do JavaScript. But it's schemaless. So you can set whatever properties make sense here. There is a syntax for deleting them. I can't remember what it is off the top of my head, but you can delete the properties too. Speaking of deleting, if you want to delete a room, you use the delete from rooms where, we all know this one. This is everyone's favorite operation. Deleting things. Make sure you put that where clause on there or you're going to have a bad day. Hashtag true story. Yeah. The warehouse was only down for 2 hours. To do this with Cypher, it's the same thing. Match where. Just like we did before, only instead of returning it or instead of setting properties, we're going to delete it. Make sense so far? It's pretty straightforward. So I've been using this syntax here. There is a variation on this syntax I want to show you. So I'm doing this match where syntax. You can also inline that. So here I'm saying match. I've created a more sophisticated pattern to match against. So instead of just matching rooms with a particular label, I can also say that give curly braces and provide properties. And the syntax for this is the same syntax you would use for JavaScript objects, where ID colon 1 is a number, or name colon, and then in quotes a string. It's the same syntax. You know this syntax already. And that allows you to match a particular pattern in the graph without having to add a where clause. This applies to create as well. Here I'm creating a room. It creates that node that matches that pattern, and then I'm setting properties on it. But you can inline that as well and say create room and just provide the properties that you want in that create. And you'll notice here that I actually am not assigning room to a variable right here because I don't need to reference it. So I don't need to assign it to a variable. And so here's a couple examples of using this syntax against our actual problem. We're going to create a monster and assign it properties, and so we're using that inline syntax for creation. And you can combine both of these syntaxes together. Here I'm creating a treasure, assigning it to variable t, some of my properties are inlined, and some of them are being set after the fact. I don't know why you would want to do this, but it might be easier depending on how your code is generating your Cypher query. So, what do we got so far? So far, we've got a relational database. It's got some tables. And there's no relationships in the relational database. We've got a graph database. It's just a big pile of nodes. There's no relationships between the nodes. Let's put some relationships and connect some of these things together. Let's put a monster in a room. They've already let me speak, so we're halfway there. So if we want to do that with SQL, we have to change our monsters table. We have to add the room ID as a column and then fill it. And so now the monsters table's got foreign keys that point to the room that monster's in. We've probably done this a few times. To do this with a graph database using Cypher, you need to create a relationship between the monster and the room. And you need to say the room contains a monster. And so the way to do that is you match the room and you match the monster. And you assign them to some variables, and then down at the bottom you call create. You reference those variables and then create the relationship between them. The variables, then since they're just variables, won't be created, but the relationship will be established between them. You might be tempted to inline this whole thing and say, well, can I just call create r::room with curly braces and contains and m::monster with the curly braces and do that? If you do that, it'll create another room and another monster. So you need to go out and reference that monster first and reference that room first. Reference the node first before you can create the relationship between them. Otherwise, it'll just create a new one. But this is how you put a monster in a room. You just match them, query them out, create the relationship you want. Putting treasure in the room is the same thing. I just kind of put this in here because it felt like I needed to be complete. And here we're creating a contains relationship with the treasure as well. So one of the things that I think is neat here is that the contains type on the label or on the relationship is the same for both a monster and a treasure. So you could actually do queries like, give me a room, give me all the rooms that contain anything. You could say that contain a node. And it doesn't have to be a node that is a monster or a treasure. So it's kind of neat how you can do queries that are harder to do in a relational database. So here's our relational database now. We've got some one-to-manys. Our graph database has some relationships, but not all the ones we want yet. We can do some interesting queries. We can start solving my problem of finding the room that has the best monsters and the best treasure. Best monsters, best treasure. That was supposed to be timed better. So, if we want to query our relational database to say farm all the XP, give me the rooms with the highest XP monster so I can go and kill it and get its XP. If I'm using a relational database in SQL, then I can use this highly inefficient query. I know there are better ways to do this. But this one's simple, all right? We just select from the tables we want, we join them with a where clause, and then we get a row. We get a list of all the monsters, all the rooms, their name, and the XP in that room. And we order it by the room, the XP descending, and it gives us like a priority list of where the top monsters are. Give me the biggest monsters first and go down. If we want to do the same query using Cypher, well, we can match a room that contains a monster. This will walk through the entire graph, find every room that contains a monster. That will match that pattern. And if a room contains more than one monster, we'll get 2 hits, one for the room A and monster B, and room A and monster C. And we'll get this nice list of things that match this pattern. We can pull out the individual fields that we care about, the ID, the name, the XP, and return them, and we can order them descending by experience points. In a lot of ways, this isn't too different from the SQL, other than the matchers and the returns are a little different, but the order by and the descending all look very familiar. If we want to get all the gold, same thing. Again, I'm a little bit of a completionist. And so, same thing. We're finding the rooms that have the best treasure in them. So far, so good, but so what? I haven't used a graph database to do anything that I can't do with a relational database. I've done CRUD operations, I've done some basic joins. That's all I've done. What happens when I want to put a room, connect the rooms together? And this is where graph databases start to get interesting. Because they're, well, frankly, it's a better metaphor for this sort of problem. If I want to have show the relationships between rooms in a SQL database, in a relational database, how do I do that? Well, I need to create something that maps a room to a room. I need to create some sort of corridors or collections or connections table. So I create a table and it's got two keys, the source room and the destination room, where it comes from and where it goes to. And then I need to start inserting rows into that table, say that the statue room leads to the barracks. And this actually gets kind of complicated. This is where I think relational databases start getting hard to think about, is when you start having these many-to-many tables. How do we do this with Cypher? You may have a guess. It's exactly the same as putting a room in a monster and putting a treasure, or putting a monster in a room and putting a treasure in a room. The only thing we're doing here is, instead of matching a room and a monster and a room and or a room and a treasure, we're matching a room and a room, and we're creating a relationship between those two rooms. So we get room 1, we get room 2, and we create a leads to relationship. And so the relationships between the rooms is created exactly the same way as the relationship between rooms and monsters or rooms and treasure, or anything else you would want to put in your dungeon. So our relational database has gotten kind of, even for this small of a problem, has actually gotten a little bit complicated. I feel like the screen looks cluttered. The graph database looks like what it is. So, how are we doing on time? I got about 20 minutes still. Good. It's super munchkin time. Let's look at some other types of queries, things that you can do in graph that are hard to do in relational databases. First thing is pathing. So I can match patterns that are arbitrarily long. So this matcher right here, that matches a room node, that matches a room node, and that little asterisk right there says match n number, as many as we can, of leads to relationships between those nodes. So this will match a room that leads to a room. It'll also match a room that leads to a room that leads to a room, and a room that leads to a room that leads to a room that leads to a room, et cetera, et cetera, et cetera. That's very powerful, because now I can do arbitrarily long queries against my rooms. In a relational database, you end up having to like CTE, or recursive CTEs, which are just complicated and confusing. Here, I put a star here, and it will match arbitrarily long things. You can, let's go. I want to say one more thing about this. Some of you may be seeing this and thinking, but what if I have a graph that's a big circle? And I say, match it arbitrarily long. Well, there's an infinite set of arbitrarily long options in a circle. It'll catch that. Don't worry, it doesn't crash your server. It won't recurse around that circle multiple times. So, but it's not very performant to do that. And so you can limit how far you want it to go. So this gives you a minimum number of hops to go and a maximum number of hops to go. So you can say, I want between 1 and 3 hops away. And so you can create a natural limit to this. So for example, we can have a query that finds nearby rooms. Here, I'm assuming I'm in room number 1, and I want to find rooms that are 1 or 2 hops away. And then I want to return the ID of that room and the name of the room. This allows me to, well, for example, say I'm in a dungeon room in the dungeon, and I'm like, well, what are the rooms that I could go to? Well, this will give me a little menu of rooms that I could go to. Don't know what's in the rooms, but I do have some ideas of what's nearby. Maybe we want to find something a little more interesting. What about the nearby room with the most gold? That's what I'm talking about. Well, here I can do that same query and just tack on an extra contains. So room that I'm in leads to 1 or 2 hops away, another room. That room must contain treasure. So if the room doesn't contain treasure, it won't match. The matcher won't match it. Then return the ID, the name of the room, and the value of the treasure in the room, because that's all I care about. Order it by the gold piece value of that treasure, descending, so the biggest one's at the top. And let's throw a limit 1 on the end, so that just tells me this is the room with the most treasure that's 1 or 2 rooms away. I've joked a couple times that I'm a completionist. I want to hit every room in the dungeon. I can do that. If I look for a room that leads to n number of rooms, as far as I can go, that's going to match every path in the graph. And I can assign that. You'll see here I've got this little p equals there. So you can capture the path information on a match, on a pattern. So this is going to create lots and lots of paths. We can assign those paths to variable p, and we can pass that into functions and get the information about that path out. So we can get all the nodes that are in that path, or we can get all the relationships that are in that path, or we can get the length of that path. And so this is going to find all the paths, and then we're going to return the nodes in the path, the length of that path, and rename it as len. And then we're going to order it by the length descending, so the longest path goes to the top, and then that should hit every room in the dungeon. This is not a very performant query, by the way, as you might imagine. We could also look for the room with the biggest treasure. So one of the things you can do when you match is you can extract variables from it. So here we're matching all the rooms that are, all the nodes that are treasure nodes. And then we got this with max right here, with max T1 gold piece. So that creates, it works just like the grouping or aggregation functions in SQL, where we want the max of all the rooms with treasure, give me the value of the gold piece that's the highest, and assign it to a variable. We can then match all the rooms that contain treasure where its gold piece value matches the max. That will give us the room with the biggest gold piece value, or more than one if there's a tie. And then we return the name of the room, the name of the treasure, and the gold piece value. And you can combine all of these things together in one super mega ultra overly complicated query. So here I'm doing the match the treasure to get the max gold piece value in the dungeon, and then I'm matching the room that contains a treasure where that gold piece value is the highest to get me a destination. That's the room I want to go to. I can then query all the paths and extract the P, where the start ID is the room I'm in, and where I'm going to stop at the room that's my destination ID, which is from the max gold piece, which is from the querying of the treasure. And then I can return the nodes in that path. And there may be multiple paths here. Return the nodes and the length. Order it by the length ascending and limit 1. This will give me the shortest path to the gold. However, this is a very slow query. Oh, yeah.
And you might have an error in the top matching if the highest rating gold isn't in a room.
Yeah, that's true. Yeah, I'm assuming that all treasure does have a relationship to a room. But you're right. If the highest rating gold is not in a room, then you won't get anything back. And it's like, it's here, but you can't get here. That's a very good point. The better syntax for this, of course, is we have a function for doing shortest path. This is a common use for graph databases. I want to find the shortest path from point A to point B, and it might not be a dungeon. It might be like a transportation network, with the nodes being things like bus stations and train stations and all those sorts of things. And with weights on the edges saying how long the road is or what the travel time is. And so if you use the shortest path syntax like this instead, you'll get about an order of magnitude performance improvement. So let's see that order of magnitude performance improvement. So I'm going to show you that this stuff is real and how you can put it in your system. I regret to inform you that my demos are in JavaScript. we have someone in here from Redis that knows how to do this from Java, so you can talk to Brian afterwards. So let's go over here. So I have created a big thing that generates random dungeons. Is that readable, or do I need to embiggen that a bit? I think maybe a little bit. So I've written a whole bunch of code, and you can go out to GitHub and look at this yourself, that generates random dungeons. I used a random name generator library and everything, and so it creates all these crazy names for everything. And so I've got a bunch of classes here. It's kind of interesting. It's fun to check out, but I'm just going to go and run it. So we get npm run generate. And so that has created a key in Redis that has a graph database. If we go out here to Redis Insight, and we go here and look at the key, you see we got a key called graph, or that's called dungeon. We can't look at that directly because it's hard to visualize, but we can go ahead and query it here. And so let's do graph.query dungeon, and then we'll do return, or we'll do match n return n. That's sort of like a select star it's sort of like a select star from tables sort of query for a graph. So we're just going to match n, return n. Match all nodes, return them. And Redis actually does this really cool thing here where it shows you all the nodes graphically. And if I click on one, here's the dusty bridge. And if I double click it, I can see other relationships here. And there's a dusty defile. We've got some monsters floating around here. Yeah, so the dusty defile contains 6 gorgons. Better watch out. It contains, what is it? Come on. It doesn't always want to click on my trackpad. Pyroboros, the displacer beast. And Seraphal, the giant rat. So good random names. The dungeon itself is the dim sewers of Ferislad. So fun, kind of ridiculous. You can do other queries here too. Let me show you probably what would be a better query, something that's a little more tabular. So let's match all the rooms. Say match r:"room, not tomb, not how you spell tomb either. And we'll return the name of the room. We'll just return the name of the room. And if I run that, it says no data to visualize, switch to the other view. That's fine. And so now I've got the big jail, the dusty bridge, the blue pit. So that's all the rooms. And you can see it's very fast. It ran on my MacBook here in 0.191 milliseconds. But let's do let's go to the JavaScript code and look at some of the other bigger queries. So I want to go into here to my little demo. If you want to do this from JavaScript, you can just use Node Redis. Here I'm creating a client, handling any errors that I might get from that client, and then I'm connecting. And then I just create a query. Here's my match the dungeon name and return it. You just call graph.query, key name, and your query, and you get results back. That's all there is to it. And so here I'm matching the name of the dungeon. Here I'm doing the slow query to find the path to the room with the most treasure. Here I'm doing the long query. These are just the queries I showed you in the slides here. So let's go ahead and run this. Run the demo. Okay, hang on. That's hard to read. Let's pipe that into JQ. There we go. And embiggen that. So here we have the result of our first query, where we're getting the name of the dungeon, the dim sewers of Ferislad. Here is the slow way of doing it. It took about 1.5 milliseconds. And then if you do it the fast way, which for some reason returned data of null. There might be a typo in my query. Yeah. I'm sure running it again will fix it. It ran faster though. I think I have a typo in my code. I changed this right before I gave my talk, and that's always the way you should do demos, right? You should change them right before you give your talk. The key point here is that it is about an order of magnitude faster to use the shortest path algorithm. I think I've got a typo in my query. I've got 5 minutes. I'm not going to troubleshoot it in that amount of time. But accessing this from JavaScript is pretty easy. Let's go ahead and just to show that this is actually generating a dungeon, let's generate a new one. And let's comment out these perfectly great queries that don't work. And save that and run it again. And we'll just get our, so now we've got a new name. If I generate again, I get another new name. The Shattered Castle of Zusoth. I never know what I'm going to get for these random names, and sometimes they're really funny. So always makes this kind of fun talk to give. Okay. So, a little demo there. Now I've given you an impractical application. Maybe not impractical. Maybe you're building some sort of fantasy role-playing game that you want to digitize, and this might be a really good application. But some practical applications for graph databases is social networks. It's the most obvious one. If you're Facebook or Twitter, I mean, I use this as examples to talk about directed and undirected graphs. They're an obvious candidate for using a graph database. A genealogy is really just social networks extracted over time. If I worked for Ancestry.com, I would kind of want to use a graph to model all that data. I suspect they probably haven't because their core system's probably old at this point, but I know nothing. I'm just talking out of my butt. Transportation networks. I talked about this example too. You can optimize routes for drivers and mass transit. And logistics is another great example. So we had a problem in the US a few years ago with some E. coli contaminated spinach. You can then figure out, well, you have a graph of stores and warehouses and farmers and trucks, and then you can track back and query it and find out where it came from. Another one that is probably more relevant in the last couple of years would be contact tracing. That's a different kind of social graph. And so there's lots of practical applications for graph databases. If you want to play with graph databases, probably the easiest way to do that would be, you want to play with my code specifically, would be to get Redis Stack. Redis Stack is the Redis you know and love. It's open source Redis with some extra modules that add some new capabilities. Redis JSON adds JSON data types. Search lets you search JSON and hashes. Redis Graph is the one we talked about today. Lets you create a graph database. Redis Time Series lets you do time series data. And Redis Bloom has a whole bunch of probabilistic data structures to play with. You can get it at that URL. I've been working at Redis for 1-4 - 1 years. We have a Discord server. I'd love to see you on there if you have questions. I'm on there all the time answering questions, as are lots of the team. The client you saw me using to query Redis Graph and just Redis in general, it's called Redis Insight. It's a nice GUI. Check it out. And go ahead and, if you don't want to install Redis on your machine, you can use a cloud version at redis.com/tryfree. And if you use the code STACK200, my boss will know that you saw my talk. If you want to check out these, you can go to this QR code to get all of this stuff. This QR code is perfectly safe to scan. It will never give you up, nor will it let you down. And that's pretty much all I have. I've got 2 minutes left. I think we'll do questions after. So if you have questions, feel free to come up while I tear down and I'll answer them. Otherwise, thanks a lot for attending my talk. I'm Guy Royse. Try Redis Graph.